Hi, welcome to part 2 of our lecture 4. So now what we are going to look is for the problem of inference after model selection. So what we saw during the first part of this lecture 4, we were not considering the model selection step when conducting inference. So in terms of statistical theory, we can say that those asymptotic results were non-uniform. Okay? So now we are going to take into account the possibility that model selection approaches like lasso or similar techniques can make mistakes and how to take these mistakes into account. Okay? So we are going to talk about one specific technique and during our live session on Friday, I can elaborate more on other possible techniques or the alternatives. But this one that we are going to see now is really simple and very effective, right? So this is based on these two papers by Alexandre Belloni, Victor Chernuzukov, and Chris Hansen, and also Fernandez Val on the second one. These papers are published in the Review of Economic Studies and Econometrica. They are both on our Google Drive, so you can go there and just download the papers. Right? So what's the idea? Suppose that we have a linear regression model, okay, and we have one parameter of interest that's alpha, okay, and this parameter alpha is the coefficient of a specific variable dt. So here we are considering the scalar case, but this can be easily generalized to a more general setup with multivariate variables. Okay, so for more than a single regressor. Okay? And we have now a vector of exogenous variables x, basically a p-dimensional vector. Okay? And these are our controls. Okay? We are really not interested in the parameter beta. We are interested on the parameter alpha. So our inference goal is to test hypotheses about the population value of alpha, and what is alpha is the impact of d on y controlling for all these axes. Okay? What's important is that the problem that I'm going to mention is not only a problem of high dimension. Okay, it can. I will show that things can go wrong even in very low dimensions like p equal to 1, but in the general setup of this course we have like p much larger than t, so we are in a high dimension setup, right? Although, let me repeat again, these problems, the problems that I'm going to show you now is not a problem particular to the high dimensional case. They can happen also with very low dimensions, in a very low dimension setup. So to illustrate, let's go to very low dimension. Let's set p equal to 1, okay, and let's consider bivariate regression. So we have two regressors, d and x. D is our variable of interest. We want to measure alpha, and we want to test hypotheses with respect to alpha, and x is just a control variable with a coefficient beta, right? And let's assume that once we control on d, the expected value of u given x is 0 and vice versa. Once you control for x, the expected value for u given d is 0. Okay? So if we correctly specify the model, we can assume that d and x are weakly exogenous. So, and these alpha and betas represent like the causal parameters. Okay, we're in a very simplified model, right? And what's the common practice? Suppose that we are going to conduct model selection. Of course, with just two variables, probably we're going to run this regression and then always include x, right? But let's say that we are going to use the usual machine learning model selection toolbox. So we only include x in this regression if it passes some kind of test. It can be a t-test, like saying we run the long regression. We call the long regression exactly this model. So this is called, that we are going to call the long regression. Okay? Long because we have our variable of interest and the control. So again, let me name this our control variable. Okay? So what we do is that we are going to keep this in our final model if, for instance, we find that beta is significant according to a t-test, or if we run a lasso regression, this beta is not set to 0. So then x is included. If x is not significant, or if lasso excludes it, we drop x from the equation, and then we refit the model, and we refit, in this case, will be the short regression. That will be just the regression of y on d, because if we say that beta equals to 0, there's no beta anymore, so we have the short regression. Okay? What's the problem with that? Okay? If beta is close to 0 and in absolute value, okay, but not exactly equal to 0, let's say that the absolute value of beta is proportional to 1 over square root of t, t being the sample size. So t here is sample size. Okay? Then the procedure can go terribly wrong. And why is that? And when it can go terribly wrong, if we want to estimate alpha correctly, this causal parameter correctly. So what do we know about the linear regression? That's the first thing that you have to bear in mind. We know that if x is uncorrelated with d, okay, let's write it in a little bit stronger condition. Okay, if d given x is just a constant, c, okay, or can be x given d is just a constant, so they are independent in mean, okay, including or not x does make no difference in terms of alpha. Okay, doesn't matter if it's beta equals to 0 or beta is not equal to 0. On the other hand, if this is not true, okay, if instead of a constant the condition expectation is something that depends on x, the correlation among the two, then if these two variables are related, okay, and so there is correlation between d and x, so they are related. So if you omit this variable, we are going to have omitted variable bias if beta is different from 0. Okay, so that's the traditional omitted variable bias that we see in any econometric textbook. Okay, first course in econometrics, you're going to learn about the omitted variable bias. Okay, if we want to estimate the causal effect, alpha. Okay, so what? So if we wrongly remove x, so then we have a problem. And why it's going to be a problem that if we try to use this first step here, or conducting model selection? Because usually model selection techniques such as the lasso will set beta to 0 if beta is small. So if beta is of order 1 over square root of t, usually lasso will make mistakes and will set this parameter wrongly to 0. Okay? And whenever it's 0, bang, we have omitted variable bias. So that's the idea of the nature of the problem here. Okay? Just to show you a simulation, let's take a simulated data. So here we have that yt is alpha dt plus 0.2 xt plus ut, and in this case d and x are related, so d equals to 0.8 xt plus vt. Okay, so dt xt are jointly normal, they both have 0 mean in this covariance matrix that you see on these slides. Okay, so let's run the following experiment. Let's set alpha equals to 0, so the true alpha is 0. Okay, and we are going to simulate 100 observations of y, d's, and x's, and we are going to run the long regression. We are going to run a t-test, simple t-test. Again, econometrics 101. We run a t-test for the parameter beta, that in our case equals to 0.2. And then we are going to test the null hypothesis, beta equals to 0. If we do not reject the null hypothesis, then we remove x from the equation and we run the short regression. And then we are going to test the second test, that's going to be alpha equal to 0 or not. So we run a test to decide if we keep x in the equation or not. Okay? And then, based on that result, we are going to estimate either the long regression or the short regression and conduct a hypothesis test on the parameter alpha. We are going to repeat these 1,000 times. And then we are going to count the frequency of times we reject the null hypothesis that alpha equals to 0. So if we are running a test at a 5% nominal level, we expect to reject the null of alpha being equal to 0 only in 5% of the cases. Okay? What happens is what we see here in the picture. So the theoretical distribution of the coefficient, the alpha, the estimates by the OLS theory will be something that will be centered at 0 and with a Gaussian distribution. What you see in practice is the histogram in blue, which shows that the estimates for alpha, the OLS estimates, are bimodal, okay, with modes completely different from 0. And in fact, what you see on the slides, that the H naught here, this hypothesis here, is rejected in about 50% of the time instead of 5. And why is that? Because we are making mistakes in the first test, in the first t-test. That's deciding whether or not we shall remove x. Okay? So then you may say, oh, but this is the problem about t-test. Machine learning is much better than t-test. Let's try with lasso. Okay, let's try with lasso, and what you see is barely the same picture. Exactly the same thing. Nothing different. Still, distribution is bimodal. The estimates of alpha are bimodally distributed with modes different from zero, far from normal, and we still reject the null 50% of the time when the nominal size would be 5%. The theoretical value that we expect is 5, and then we get 50. Okay? So it's clear that we have a problem. Okay? How to solve this problem? Very simple idea. Something that's called double selection procedure, and was proposed by Alex Belloni, Viktor Chernusukov, and Chris Hansen in this restudies paper in 2014. So the idea is the following. We are going to include the controls, the x variable, if it's a significant predictor of y according to some conservative test. Okay, so that's what we have been doing so far. We are estimating the long regression. So this is about the long regression. Okay? So we are estimating the long regression, and we check if x is significant in this long regression, either by a t-test, by a lasso, adaptive lasso. You can pick your favorite model selection tool. Okay? So we include x if this is true, but we also include x if it's significant predictor of d. So we are going to run a regression of our variable of interest d on all the controls on the axis, okay? And if any of the x's appear to be significant, we are going to include them. So we are going to test in two equations. So that's why it's double selection, because we are testing, we are selecting x in two equations. Okay? On the long regression of y on d and the x, and on regressions of d on x. Okay? So then we refit the model after the double selection, and we can use standard confidence intervals. Why this will work? Because we have to multiply by 2, like the number of errors that we have to make, in order to wrongly remove x from my equation. We have to make a mistake that x is not relevant in the long regression of y on d and x, and you have to make a mistake also on the regression of d on x. Okay? And because of that making the mistake twice, I'm going to show you the intuition why the method will work and why it's going to be better. Because one can say, oh, you're just amplifying the error. You're running more model. There's more model selection going on. Why are you reducing the error and not amplifying it? So let's see why. Okay? And this above procedure, it will work both in low and high dimensions. Okay. Of course, in high dimensions, we need some sparsity or weakly sparsity assumption. Okay. But nothing more rigid or stronger than what we have been imposing during the previous lectures. Okay. So now takes the same example, that the same simulations, but instead of doing the single selection, let's do the double selection and compare the theoretical distribution with the empirical one. And what you can see on the slide is that, okay, we are now bingo, right on target, right? So our empirical distribution, represented by the blue bars, can fit almost perfectly the theoretical distribution represented by the red line. Okay? And we can do this by t-test or lasso, same result. Okay? So why is that? So again, his intuition is via omitted variable bias. So again, let's have the regression of y on d and x. That's the model. Let's assume that this is the truth. Okay, and now let's write a model relating d with x, and then we have this parameter gamma here, and this parameter b key, and also this parameter b key. Okay, so we have these two models. Okay. Assume now that instead of running the long regression, okay, we are regressing y on d. So basically, we have a combined error. Let's call this ET. Okay, that's beta xt plus u. So we are running the regression yt alpha dt plus ET. ET is defined as here, okay? And we want an estimate of alpha. This alpha here, the true alpha. Okay? What we know from basic econometrics, okay? That the bias alpha hat, that's the OLS estimator. So this is OLS estimator on the short regression. Okay, so alpha hat minus alpha multiplied by square root t, t sample size, will be given by d prime d. What's d is just a matrix stacking all the observations of d. Okay? So the d transpose d divided by t inverse 1 over square root t d prime this v here, which is exactly this error here. So let me, sorry about that, let me say that this v here is exactly the epsilons stacked. Okay. Different letter, but I started with a different letter here, so let's keep a different letter here. So this is kind of the good term. That's what we get from OLS, right? We can, during the live session, if you have doubts on that, I can go through the derivation of this term. So this is the good term. And then we have the bad term. What's the bad term? The bad term is the omitted variable bias. Because what will happen here is that this omitted variable bias will be 0 only when this gamma is 0, so d and x are not related, or beta equals to 0. And this becomes clear because of this term here. Okay? So what happens if you make a mistake and you exclude x, in the case when neither gamma or beta are 0, then we are going to have a bias term. So this kind of is the very bad term in your alpha hat minus alpha expression. Okay? Hope that's clear. So the good term is asymptotically normal. Okay? We know that because this will be this will converge by the central limit theorem to a Gaussian random variable. Okay, so this good term here will be asymptotically Gaussian. Okay, and the bad term to vanish. Okay, what do we need? We need square root t gamma beta to go to 0. Okay? Because if this is the case, and why we have this square root t? Because we have the square root t here. Okay? So we need this to go to 0 in order to avoid the problem in the asymptotic distribution of alpha hat, the problem that we saw before. So what happens is that a single selection method will drop x from the equation if beta is of the order 1 over square root t. Okay, so if beta is of the order of square 1 over square root t, it will drop x from the equation, so we are going to have this bad term here, no matter what's the order of gamma. So the bias term, this term here will be, it won't vanish, it won't be 0, because what we are going to have here is going to have square root t, gamma, and something that's of the order 1 over square root t, which is not converging to 0. It's converging to a value that's different from 0. Okay? But double selection will drop x from the equation only if beta is small, but also gamma is small. So we need both gamma and beta to be small. So we have something here that's 1 over square root t, 1 over square root t, we have square root t here, so this overall term here will be of the order 1 over square root t, and this goes to 0, bingo. And then we have our result. Okay, so because we need to make the mistake 2 times in order to drop the variable from the model, we are going to save our inferential procedure in the end of the day, right? So the idea is really simple, and the intuition is also simple. We can come back to this during our live session on Friday if you have any doubts. Okay? But that's basically the intuition behind the method. Of course, to prove the result, the math is quite complicated for like general methods, general model selection techniques, but the intuition, on the other hand, is quite simple. And the main theorem from their paper is that once you do the double selection, then you're going to have the usual central limit kicking in, so alpha hat will be asymptotically Gaussian, and that's it. And you can use just the standard inferential procedures that you do when you're conducting a t-test if you use double selection. Okay? There's in their paper they show a more interesting simulation. Now X is large dimensions, like we have like 200 regressors, 100 observations, and they consider also situations where beta is not truly sparse but just approximate sparse. So the beta j is of the order 1 over j squared, so j is just the index of the variable, and also the gamma j is also the index 1 over j squared, right? And they calibrate the model in order to the R square in the regressions to be 0.5. Okay? And all the regressors are correlated Gaussians. Okay? And what they show is that when you do double selection, the empirical distribution of the estimate for what? They estimate for alpha. Okay? That's the blue histogram. And the theoretical value that's Gaussian is the red line. So you see that's right on spot. Right? So the standard normal theory, the standard regression theory works just fine here if we use double selection. If we use a single selection, then things start to become a little bit uglier. So again, we have some bimodality. So single selection, bad; good selection, good. Okay? Single selection, bad; double selection, good. So that's the message. Okay? They also show an application that's basically the effects of abortion rates on crime, the US. So Y is like crime rate, D is changed on the lagged abortion rate, and they have a bunch of controls on the X, so they can have like many controls. So just to go quickly here is basically to show that if we don't include any control, you see a significant effect of abortion on crime reduction. If you include the flexible controls, the effect is even larger, but it's not statistically significant because you have a large dimension set of controls. And if you take the flexible controls and you do the single selection, you go back to the basic controls thing. But when you do double selection, then you see quite a reduction in the effect, and the effect are now not to be significant anymore. So just for you to show that when you do inference correct, maybe your conclusions can be quite different. Okay, so this is the application that they have on the paper. Okay? What's going to happen now that in our block 3 we are going to look at financial application of these methods in terms of selection of factors in an asset pricing model. Okay, so see you soon on our third block. Bye bye.